So in part 2 here, we're going to look at baking our pivot data to our UV of an object we either create or import into Houdini. The first thing we need to do, though, off the bat is discuss a behavior with Houdini that I do not like involving geometry that you import. And I'm going to start creating a geometry here based off of a cone that so we can actually witness this and see it. What's basically going to happen here is that as I export this file, I'm just going to export this cone here with a Z up axis, so that it's Z up as it's being treated. And I'm going to export that here. We're going to call this upverify.fbx. And if I bring that into Houdini here, using a geometry node and then a geometry SOP, and then we're going to use a file node, we're going to see something strange. So if anybody is familiar with Houdini, understands that Houdini prefers the Y up orientation by default. And you'll notice that our cone looks like we would have expected it to, with it pointing upwards. But the thing to be aware of is that it is pointing in the Y-axis positive, meaning that if I jump over here to like Unreal, for example, I'm going to import that same file we just looked at, or we just created, and I'm going to make sure that I don't convert the scene. We will end up with a geometry here that is pointing Z up as we expected. But if I take this same geometry that I just imported into Houdini, meaning that we just have a file node here, all we've done is bring it into here. If I take this node and I export it from Houdini directly out, and I'm going to call it here up test from Houdini, export that, and I import this one into Unreal. So again, I didn't make any changes. I didn't move a single vertex around, a single point around, that kind of thing. If I import this and I do not convert my scene, you'll notice that our geometry here is now sitting on its side, meaning that Houdini itself has manipulated the positional data of our object, so its position may not correspond anymore to the baked vertex positions. As far as I know, there is no way to override this as far as an import goes on Houdini. So what you need to make sure that you do, if you need to use this file again outside, or if you want to keep this consistent with other versions and other projects, the very first thing you would ever need to do from this is use a transform node and rotate this object 90 degrees in the X. And this will give you a Z positive, so that it is now existing how we were expecting it to in the first place. There is one other way to import a FBX into Houdini. You can go to File, Import, Filmbox, FBX, and you do have more options here, including a Convert to Y up coordinate system, where you can uncheck this. And we can select a geometry here and import it that way. The issue is, if we do this through here, if I import that same file, that same cone, just clicking on import will create a new subnet inside of basically a new geometry. And so unfortunately, if you're trying to set up a system basically where you can just plug in and have like this quick script that we want to run for our geometry, just for each different geometry, this is relatively obnoxious for purposes of importing and such, because it's going to create a new node, or it's going to create a new subnet on the object level every single time. My last note before we get started is that in order to actually export what I'll be showing you today, you will need at least the educational or a limited license version of Houdini. The apprentice version, while it will let you do everything I'm showing you guys in Houdini, it will not export the FBX at the end for you. That's something that apprentice cannot do. So to start talking about creating our short script to bake our pivot data to our UVs, we need some geometry first. So what I've done here, just to prepare, is I have two different geometries. One is the default crag geometry that is inside of Houdini. I then use the RBD material fracture node to split him up into smaller pieces, and I finally rotated him 90 degrees so that he would lay in a Z up axis. I also had here a cube. Both of these objects I've scaled 100 times, but this cube I also ran through that same RBD fracture node just so we can get pieces out. So the idea here then is for each one of these separate pieces, if I use here an explode node, so we can kind of see it, I basically want to get the centroid of every single one of these pieces and somehow bake it to the UV. We can even see what the centroids might end up being by using the extract centroid node. I can then look at that, use this. I will put the exploded view on our secondary, our template view, and then I will use my primary view for our centroids, and we can see that this node itself, the extract centroid, will give us the data we exactly want for all of our pieces. You can see here, if I'm kind of mousing this around a little bit, that this is generating the pivot points, or the centroid, of every single one of these pieces we have. So we somehow need to save this data to each vertice that we have. And we're going to do this by using a for loop. Now there is the for each primitive, and we can use that in this particular case, but there'll be one problem with it. If I connect this to my fracture node, and I look at this, if we take a look at a single pass here, let me turn off the template view of exploded view, you'll see that if I go back to our box, we end up, actually make that there, we end up looking at only a single plane if we look at each one of the passes. And that's not exactly useful. What we could do is, because our RBD material fracture gives us this information, we could change it to our piece attributes that we use something called name. And then it'll start giving us the entire actual connected piece. So now if I pass through here, we can see that it's starting to give us each separate piece. In fact, if I pipe in the exploded view instead, we can even see a little bit more easily that we're actually just now iterating through every single separate piece. This is because if I split my pane view here, and I change this to my geometry spreadsheet, every primitive from after the RBD material fracture is given a name, and it's given a name based on its piece value. So this for loop is basically using that, and it is now looping through and showing specifically those with that name. Now this is fantastic if we're using the RB material fracture, but what if we are specifically looking for something so that we can bring our model in from Maya, it's already been fractured there, or some other program? Well, in that case, you're going to want to use the for each connected piece. And this is going to have an extra little node at the top here that we can just plug in directly, and it will create its own attribute, you'll see here class, that it will use for that same purpose. And if I use this same exploded view here, we can then see that if we go to a single pass of this, it's doing the exact same thing, which is basically letting us iterate through each individual piece. Which means that if we then use our extract centroid node, we could technically look at a single centroid at a time. So what we're going to do is make sure that this node here, this extract centroid, is inside of here so that we know that we're going to get our centroid every time we want it. Now the only catch is we can't just use that, because if I just pass the extract centroid through here, I'll end up with just a single point. So there's obviously more we need to do inside the for loop. I'm also going to get rid of this exploded view because it is going to mess some things up for us afterwards. So the next thing we want to do then is we want to make sure that we have a place to save this data to. So we actually need to make sure that before we adjust this connectivity, we're going to UV unwrap this. And you'll have to do this 2 or 3 times. It depends if you've unwrapped it once so that you have something for textures and materials in your other program, like if you're bringing this in. if I look at my vertices sheet for my geometry, we can see that I just created the UV effectively 0 here. And I'm actually going to copy this node 2 more times. And I'm going to unwrap this thing 2 more times. The second time I'm going to call it UV1. The third time I'm going to unwrap it, I'm going to call it UV2. So now I have a bunch of extra UV channels of data on every single vertice that I'm going to begin writing information to. We're going to write information to here using an attribute wrangle. And we're going to put this attribute wrangle inside of our for loop. And what we're going to do here is we're going to take that centroid information that we saw, the one that we got for every single pass here, and we're going to plug that into our attribute wrangle's second input so that we can utilize it there. And so now here's where, if you have experience with Vex, you'll probably follow on easily. If you do not have any experience with Vex, Vex is basically a C++-ish style programming language that you can use inside of Houdini, and it lets you do things like this, where you want to create your own kind of procedural work. For example, in our case, I specifically want to run myself over each vertice, because I want each vertice to eventually store or modify the data here. And so to start writing our Vex code then, the first thing I want to do is verify that we can change this UV1 and UV2 data to whatever it is we want. So the first thing we're going to do is we're going to grab ourselves the set vertex attribute function. And what I'm going to do here is I'm going to click on it. I'm going to click F1, and this is going to bring up the Houdini in-program help. And this is going to let us know what exactly this particular function is going to request. And it's going to want the geo handle, which is, for our case with attribute wrangle, is specifically which pin we want to pull data from. It wants to know the name of the attribute we're trying to adjust. In our case, we're going to look at UV1. It wants to know what primitive number we're working on. That's going to be -1 in our case. It wants to know the vertex number, and it wants to know the value that we want to set it to. So I will type in 0 for our pin 0. The name is going to be UV1 for the attribute that we're trying to adjust. I mentioned that we want to use -1 for which primitive number we're going to use. And then for our vertex number, I'm going to use @VTX num. That's basically a @vertex number. And that's basically whatever iteration, whatever vertex iteration we're running through, that's what we're going to use here. Finally, the value. For this test here, I'm going to set this to 0, 0, just right off the bat. And I click down here, and we're going to see that this immediately changed to 0, 0s. So we're affecting the right channel. I could change this to @VTX num also. And then you'll see that each value is being given something different. So we're getting the right one set. The next thing then we need to do is we actually need to pull in our centroid data. And for this, since we have this being plugged into the second pin, we're going to actually just make ourselves a vector here. We're going to call this variable here centroid point. I'm going to set it equal to point, and I'm going to tell it that I want to use pin 1. I want to use whatever its position value is, and then 0. Specifically, we can hit F1 on this as well. What it basically is asking for is, geometry, attribute name, and then which index is it we are looking for. It's the point number. Since it's basically the centroid is only producing 1 point, we know that we just want pin 1, whatever its position is at point 0, which is it's only going to have one specific point there. And then this is going to give us a vector. This is going to give us basically a tuple with a size with 3 different entries into it. But remember, I specifically used this set option over here with 2. So we have to basically set this data with only the first 2 values. So I'm going to make myself a couple different vector 2s here. So this is going to be vector 2 UV1 data. And I'm going to make a vector 2 UV2 data. I'm going to set this first one equal to our centroid point 0 and centroid point 1. So I'm going to reference the first 2, the x and the y, and that's what I'm going to store in there. And the second one, I'm going to set this to my centroid point 2, which will be our z-axis, and then the value 0, because I'm not really using that. What I can now do is I can then set, instead of doing a set value here, what I will do is I will set my UV1 data on my vertex to UV1 data. I will then copy this line and we'll change this to UV2, and I will change this to UV2 data. And now we are storing our pivot data in our vertice. So if I take this off of single pass, all of our vertices now should have what our UV data is, or where that point is. And because it's always important to double check your data to make sure you're producing the right values, what we're going to do here is add a little bit of an extra script here at the end, just so we can visualize the points in space that we have now added to our object here. So what I'm going to do here is I'm going to add in a group node just so that I can label all of my old points. I'm going to label them old. I'm going to add myself in an additional attribute wrangle here. And we're going to collect the data now from all of our vertices. So I'm going to give myself 2 vector 2 data values here. I'm going to call this one UV1. I'm going to call this one UV2. And we are going to set these both equal to their respective values on their vertices, making sure I run this over vertices rather than points. So I'm going to type in vertex, and we know we want geoself. I specifically want UV1 for the top one, and I want whatever vertex number we're currently on. And then I'm just going to copy this to make it a little bit faster. And we're going to change that to UV2. Now I'm going to make myself a standard 3 vector here, and I'm going to set this equal, I'm going to call this pivot, and I'm going to set this equal to UV1 0, that's our x value, UV1 1, that's our y value, and UV2 0. That's our z value. Remember, our UV2 1 index is not used. And I will simply add point, and I will add a point to geoself for every single vertex, and I will place it at my pivot. I don't really care if I have multiple points that are kind of overlapping each other. The idea is as long as I see them all in the right space, I know that everything is working properly. And so we won't see anything because they're all inside of the geometry right now. So the last thing we need to do here, just to verify what we're doing, is blast away all of our old group. And I will put our previous node on template mode, and we can now see that we have our pivots for each piece being stored here. Now this is a very good point in time to actually mention that this data is hard-coded into our UVs, meaning that if we, for example, were to translate this object, if I just, for example, put in a transform node here, And I can then slide this geometry around. And my pivot data stays put. It has been hard-coded to be relative to our object. So if our object moves, our pivot data does not move. So this is very, very important. So that's all there is to it then. It's actually a fairly simple system. I'm just going to have a null point here that I can pull out that I can then use to export my FBX. What we can do here is we can plug in, instead of a cube, we can plug in our crag model here, sitting over there on the side. We can even take a look that his points are being baked to his right positions as well, and they are. What I can do here is I can make this my primary node, and I can now export this as an FBX. So that's exactly what I'll do. Export, Fillbox FBX, and I will go put him in my right folder. We'll call this crag example bake. And I will export it. In the next section, we will look at bringing this FBX then into Unreal and how we can then access the data that we've saved to it inside of our shader.